If you're enjoying Why This Universe, there's another University of Chicago podcast network show that you should check out, and it's called Big Brains. Big Brains brings you the engaging stories behind the pioneering research reshaping our world. Change how you see the world and keep up with the latest academic thinking with Big Brains, part of the University of Chicago podcast network. You may have heard that by looking into space, we are actually looking into the past. And that's because light takes time to travel to us. It has finite speed. So by the time the light from a faraway part of space reaches us, it's actually an outdated picture of what its source looks like. So with this in mind, you could ask what would happen if we pointed our telescopes to the farthest possible point in the universe, the edge of the universe, so to speak. Whatever we saw there would show us what our universe looked like as close to the Big Bang as we're able to see. So today on our show, we are going to talk about exactly that, the oldest light in the universe, what we call the cosmic microwave background, or the CMB. And we'll talk about how it became a treasure trove of cosmological insight. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
So before we get into everything we now know about the CMB and all its glory, it's something special to appreciate that the people who actually discovered this thing had absolutely no idea what they were looking at.
Let me paint a picture for you. It's 1964. There are these two scientists, astronomers working for Bell Labs out in New Jersey, Arno Penzias and Robert Wilson. And they've been given access to this new radio antenna, radio receiver in Holmdel, New Jersey. And they're excited because they're going to go and point this thing up in space and look for radio waves from the Milky Way. And hopefully they're going to detect all sorts of bright radio sources and learn things about energetic processes going on in space. And it was, great success. That's what they were, had in mind optimistically. But the longer they used their antenna, the less progress they made. In particular, like imagine you turn on your old-fashioned like television with rabbit ears or something, and like you just can't see the TV program because there's all this like white noise, hiss, static, whatever. That's a pretty lousy TV. And Penzias and Wilson are using this radio telescope, and all they can get is this hiss, this buzz, and it's in all directions. They point it, and it doesn't matter if it's daytime or nighttime or what time of year. They just keep getting this hiss everywhere, no matter what. And for a while they thought maybe it had to do with like the bird droppings that accumulated on their antenna. They didn't know what it was, and they tried everything, and nothing worked. Turns out that the thing they were detecting was way more interesting than anything they were looking for. They hadn't just discovered something, going on in our galaxy or our solar system or even our corner of the universe. They were discovering the light, the radio waves that were left over from the Big Bang, from only a few 100,000 years after the Big Bang, 13.8 billion years ago. It was probably the biggest astrophysical discovery in decades in either direction, and they totally stumbled on it by accident. So Penzias and Wilson are looking at this signal. They don't know what to make of it. So they start asking around. And one of the people they asked about like what could this be was a theoretical cosmologist at Princeton, Robert Dicke. And the version of the story I've been told anyway, I don't know how much of this is legend and how much of this is truth, is that Dicke just instantly knew exactly what they had detected. After all, he knew about the arguments based on Big Bang nucleosynthesis, that the early universe in the Big Bang theory had to be hot, and that light should still be with us today. And people had, including Dicke, had made estimates for how hot this radiation should be, and they were kind of all over the map. But is kind of in the ballpark of what Penzias and Wilson had seen with their telescopes. So Dickey got excited, and Dickey and his people, along with Penzias and Wilson, started to prepare a couple of papers. Ultimately, these papers came out. One paper just described the detection, the observation, and the other one interpreted it in terms of the Big Bang. And this is really the turning point in cosmology, where you could see the Big Bang rise to prominence, becoming the standard theory, and competitors like the steady state cosmological theory started to go away because they could not explain this. So Penzias and Wilson wound up getting the Nobel Prize for this discovery in 1978. I have some mixed feelings about people getting the Nobel Prize for things they didn't even try to do, but all the same, it's such an important discovery. I can't, and they were always good natured about it. And all their interviews are like, yeah, we didn't even hear of this cosmic microwave background. We never thought about looking for this.
I feel like that just shows that the issue is with the structure of the Nobel Prize, not that they don't deserve recognition for like a great accident. Because
yeah, for sure. I mean, they did nothing wrong. They did their job very well. I'm happy to tip my hat to those guys. But yeah, the Nobel Prize probably shouldn't be the only standard for scientific excellence. There are a lot of people who don't benefit from its structure, for sure.
And also it takes something to, make the mistake. It was an accident, but in order for it to be a successful accident, they had to realize that there was something to that static that they were hearing. They had to actually analyze it.
And if they hadn't been good radio astronomers, they wouldn't have found it either. They didn't have to know what they were looking for, but they had to look well. As a little side note, historians of science now are pretty convinced that other groups of astronomers maybe had seen the cosmic microwave background at earlier times, but no one knew what it was, and certainly it didn't reach widespread prominence among cosmologists. So it's kind of, if a tree falls in the forest and no one's there to hear it, does it really make a sound? Well, until Penzias and Wilson, cosmologists had not appreciated that this signal had been detected. So I still think Penzias and Wilson deserve the prominent place in scientific history.
So we now know that the staticky signal Penzias and Wilson saw was not the result of bird poop, but was actually light from the earliest moment in our universe's history that we could possibly access directly. And remember, when they made this discovery, they really didn't know much about what this signal was. So let's fast forward to what we know today. And let's start with the most basic question of all: why does this signal exist? Turns out the answer is a little complicated, so bear with us.
All right, so our universe today has a certain amount of matter in it, an average density throughout all of space. And it turns out to be the equivalent of a little more than 1 proton of mass per cubic meter on average. But our universe has been expanding over time. So in the past, the density was higher. There was more matter per volume in the past, just because there was less volume to put that same amount of matter in. For example, over the last few billion years, any given volume or any piece of space has had its volume increased by about a factor of 10. So if you go back a few billion years, the density was 10 times higher than it is today. If you go back much farther, say only a few 100,000 years after the Big Bang, 13.8 billion years ago, then you'll reach a point where the universe was a billion times smaller by volume. So the density, instead of being 1 proton per cubic meter, was more like a billion protons per cubic meter.
So in other words, as the universe expands, the density of matter becomes diluted.
But it turns out that it's not just matter that's important for cosmologists in our universe. In addition to matter, there's stuff like light, photons, particles of light. And there are other kinds of particles like this that are moving at speeds close to the speed of light. So for better or worse, cosmologists like to call these sorts of particles radiation. So whenever we say radiation, what we mean is basically stuff moving at really high speeds, whatever that stuff happens to be.
For example, radiation usually just means photons or particles of light, but sometimes cosmologists will call rays of high-energy electrons or muons radiation as well, as long as most of their energy is in their kinetic energy or motion rather than in their mass. Okay, so some of you may be wondering, if Einstein's famous E=mc² equation told us that matter and energy are just two sides of the same coin and are really equivalent in a lot of ways, then why do cosmologists bother differentiating between matter and this radiation? And the answer is that the two actually react differently to the expansion of space.
If I take a piece of matter, something moving slowly like a proton or maybe a particle of dark matter or whatever, and the space around it expands, the amount of energy stored in that particle doesn't change.
And this actually works differently for radiation. Radiation is made up of massless or, near massless particles, so all of its energy is actually stored in its motion. If you think about this radiation as waves, you could also think about its wavelength. The longer the wavelength of radiation, the less energy it has.
So as space expands, it stretches the wavelength of that photon, reducing its energy and causing it to evolve in a different way than if it had had its energy stored in mass instead.
Okay, so why does this all matter, pun intended? Well, if we look at our universe today, there seems to be a lot more energy stored in matter than there is in radiation. But since radiation loses energy faster than matter during expansion, this means that if we go back in time far enough, we get to a point in our universe's history where there was actually more energy in radiation than there was in matter.
As it turns out, that point is about 50,000 years after the Big Bang or so, where there were comparable amounts of energy in both radiation and matter. So as space expands and all this radiation is losing energy, we can think of its temperature as decreasing. So like today, the radiation around us is all really, really cold. But billions of years ago, it was much hotter. So for example, let's go to a point about 300,000 or 400,000 years after the Big Bang. At this point, all that radiation was thousands of degrees. We know that because, as we talked about in the last episode of Why This Universe, the nuclei that make up the light atoms in our universe, those things were formed through fusion in the first seconds and minutes after the Big Bang. And that means that in those seconds and minutes, the universe had to be hot enough for nuclear fusion to take place, like the kinds of temperatures you find in the cores of stars. So it was like, billions of degrees back then. So by a few 100,000 years, it wasn't billions of degrees anymore. It cooled quite a bit, but it was still hot, a few thousand degrees. And it turns out that a few thousand degrees isn't just any old temperature. It's a very special temperature. I'm fond of calling it the melting point of atoms. Now, Shalma, I bet in none of your physics classes has anyone talked about the melting of atoms, right?
No.
So this is my kind of thing. I think it's a good way to think about it. But if I just take a bunch of atoms and I just heat them up, around a few thousand degrees, those electrons bound to those nuclei that make up atoms, they just start falling off. They start breaking up. So instead of having a electrically neutral gas of atoms, once you cook these things up to a few thousand degrees, you end up with a charged or a plasma of electrically charged particles like protons or nuclei and electrons. So at this really key juncture in cosmic history, when the universe was a few 100,000 years old and a few thousand degrees, the universe underwent a huge transition. Before this transition, all of space was filled with charged objects like electrons and nuclei. And after this transition, the same universe was filled with electrically neutral atoms. The reason this is so important is because in a plasma, light simply can't propagate. The universe is opaque when it was filled with a plasma. If you tried to take a flashlight and shine it through space prior to this transition, that light would just go nowhere, just scatter around and bounce off all those particles. But after the neutral atoms had formed, the light can basically pass through space unimpeded, making the universe basically transparent. And suddenly a huge amount of light, all of this light was released into space all at once, and it's been traveling through the universe more or less, in straight lines ever since, filling the universe to this day with a background of cosmic radiation that traces its origin to only a few 100,000 years after the Big Bang.
This is kind of related to something we mentioned in our standard model episode, which is that the photon, aside from being the particle of light, is also the carrier of electromagnetic force And
That's right.
so in a universe where there's charged particles everywhere, that light is like getting attracted and repelled by things all around it. And in a universe filled with neutral atoms, the photon will go straight through like unimpeded.
That's exactly right. Yeah. So when this light was released into the universe a few 100,000 years after the Big Bang, it was thousands of degrees. But as that light traveled through the universe and space expanded, that expansion stretched all those photons by about a factor of 1,100, cooling them from a few thousand degrees to under 3 degrees.
Yeah, maybe we should clarify. We mean 3 degrees Kelvin. So like 3 degrees above absolute zero, like unimaginably cold.
Yeah, I mean, it might be 3 degrees Fahrenheit in Chicago on a given day, but this is much, much colder than that, right. What we're talking about. Yeah, 3 degrees above absolute zero. Cold. So all this light's still there. It hasn't gone anywhere. It's been diluted as space has gotten larger, and those wavelengths have been stretched, but it's still there. We're bathed in it right now. These photons are traveling through space everywhere around us in every given moment of every given day. There are about 411 of these photons in every cubic centimeter of space today, and they're about 2.73 degrees. So these are really cold photons. In terms of their wavelength, they're in the radio or microwave range. They're about 2 millimeters long, which is, thousands of times longer than visible light, or equivalently thousands of times less energy than photons of visible light.
So this is what made the signal that Penzias and Wilson saw seem so staticky. After all, these photons are coming from all directions, and they're incredibly cold or low in energy. And since that original discovery of the CMB, lots of people have been measuring and studying it in more and more depth. By the 1970s, the CMB was modeled so well, and it matched the theory so well, that it basically elevated the status of the Big Bang to true scientific consensus. We talk more about that in our previous episode.
And then moving forward, we've transitioned from a point where the CMB was important to confirming that the Big Bang happened to our primary way of learning the details about the Big Bang. Things like how fast has the universe been expanding over cosmic history, what kind of stuff, what the composition of our universe is, even what the shape or geometry of space and time are. All of these things have been answered by cosmologists studying the light that we call the cosmic microwave background.
So how is it that some fuzzy light in the background of our universe is answering so many deep cosmological questions? It turns out all of this insight can be drawn from the properties of the light from the CMB.
So one of the key features of the cosmic microwave background is that it's really, really uniform. If you point your telescope in one direction in the sky and measure the temperature, you get 2.73 degrees. And then you point in some other direction, you get 2.73 degrees. It's 2.73 degrees above absolute zero everywhere on the whole sky. In fact, we know today that the hottest and coldest spots in this background of light are about hotter or colder than the average spot by 1 part in 100,000 or so, or 1 part in 10 to the 5. So really uniform with tiny little variations. But if you could measure those variations and map them on the sky, you can learn a ton about our universe. So let me give you an idea of why that is. To do that, let's talk about what gravity has done to our universe over time. So what gravity tends to do is it tends to take regions that have a little more matter than average and make that matter collapse, getting dense in those regions. So if you started with a universe that's really smooth, over time, gravity will tend to make it clumpy. And we can look at our universe today, and it's pretty clumpy. We don't have a smooth background of matter. We have like galaxies, and we have clusters of galaxies with a lot of empty space between them. So we know how clumpy our universe is today. We can use the laws of gravity to kind of run that backwards and deduce how clumpy the universe would have had to have been when it was young to explain what we see today. And it turns out that if the only matter that exists in our universe were atoms, then the clumpiness in the cosmic microwave background should be like 1 part in 1,000. But it's not. And by the 1980s, it was clear that wasn't the case. And then we found out that it wasn't even there at 1 part in 10,000 and tens of thousands. And it wasn't until the early 1990s that we started to see these temperature anisotropies, these variations in temperature. And by then, we knew that the universe couldn't just be filled with atoms. Other stuff had to be playing a big role. In particular, you needed a lot of dark matter. So our modern understanding, aided by these observations of the CMB, is that what happened is the dark matter collapsed first, making dense halos that attracted the atoms, and the atoms fell into those halos, making galaxies. So dark matter, in this sense, plays the role of scaffolding on the large-scale structure of our universe. When we look at it with our eyes, we just see the atoms, but the dark matter is really what formed it in the first place, and it's what holds it together now.
So the temperature variations in the CMB don't just tell us about some early point in our universe's history, but they also tell us about the evolution from then to now, how the universe became clumpy enough to have the galaxies that we see today.
So the hottest parts of the CMB are also the places in the early universe that were the lowest density. Again, it's not very low density. It's just lower than average in 1 part in 100,000. And then in the other side, the coldest parts of the CMB are the places that the highest density, again, just a little bit more than average.
Wait, that sounds kind of opposite.
Yeah. For years, I thought it was the other way around, but it turns out it is the opposite way. What's going on is if you have a place in the universe with a little more density and you're a photon from that place, when you try to escape from it, the gravity of that higher than average density place pulls on the photon, stretching it, making it a little colder. So cold means high density, hot means low density.
Okay, so an interesting interjection from general relativity.
Literally, I had a PhD in physics before I learned that I had that all backwards. So
physicists call these temperature variations temperature anisotropies, just to be annoying, I guess. But to actually detect these variations or anisotropies, you have to have a really detailed measurement of the CMB, and that's pretty hard to do.
So in the late 80s and early 90s, we started to be able to actually detect these temperature anisotropies for the first time. The first experiment to do this was something called COBE, COBE, which stands for the Cosmic Background Explorer satellite. This did a ton of science, but the two main things I want to talk about today is they measured the spectral shape or the spectrum of this light. And it's the most perfect blackbody spectrum that's anyone's ever observed anywhere in the universe ever.
The blackbody spectrum is basically how physics tells us hot objects should radiate light. But normally we only see imperfect versions of this in real life. With the CMB, it's nearly perfect.
It's this perfect, realization of a theoretical idea. I remember seeing a seminar or a colloquium or something on this topic when I was in grad school. And the person said, okay, here's what the theory curve predicts the CMB should look like. And he said, now I'm going to advance the slide and put the error bars on this. And he did, and nothing happened. And that's because the error bars are smaller than the width of the line. It just is a nearly perfect measurement. And this is because of COBE. It's still to this day, the best measurement of this aspect of the CMB. The other really important thing that COBE did is it, for the first time, could tell that some parts of the cosmic microwave background were a little hotter or a little colder than average. Before this, there was no way to detect those 1 part in 100,000 temperature variations. And that measurement led to the Nobel Prize in Physics for George Smoot and John Mather back in 2006.
So COBE was able to really see those temperature variations that have been so helpful in teaching us how the universe developed fresh out of the Big Bang to today. But COBE isn't the only CMB telescope to exist.
So whereas COBE was a series of instruments on a satellite, the next really big development in this game was carried out in a series of high-altitude balloon flights in 1997, 1998, and 2003. And this instrument was called Boomerang, and it's some horrific acronym. I'm not even going to try to figure out what all those letters stand for, but it stands for something. But we just call it Boomerang. And the important thing they did is they measured those temperature variations in a lot more detail than COBE could do. And they found that the most prominent high and low temperature patches in the cosmic microwave background were roughly a degree or so in spatial extent. So this is like, twice as big as the angular size of the sun or moon, to give you an idea. So if you looked at a map, if you looked upward to the sky and could see the cosmic microwave background with your eyes, you could see all these tiny temperature fluctuations. You'd find that the hottest and coldest patches would be, a little bigger than the sun or moon in angular extent. So this is important for kind of a weird esoteric reason, but you can use this information to deduce the shape or geometry of our universe.
So we're used to learning about flat, or what we call Euclidean space, in school. Basically, the math that tells us that parallel lines never cross, for example. But it turns out that's just one kind of space, and space could also be curved. So in curved space, parallel lines actually would meet eventually. This also means that if we lived within curved space and we looked at something really far away from us, its size could actually be distorted. So because of this feature, we can actually look at the CMB and use it to determine the curvature of our universe.
So by measuring that those patches of the cosmic microwave background were about a degree, we could deduce that our universe was approximately spatially flat or Euclidean. And that was the first time we ever learned that. So the next big instrument to measure the details of the cosmic microwave background was called WMAP, the Wilkinson Microwave Anisotropy Probe. This was a satellite experiment. It was in orbit between 2001 and 2010. It looked at the whole sky, had really good angular resolution. It could see variations in the sky down to a small fraction of a degree, unprecedented precision, and it really brought in the age of precision cosmology. Before this, we were lucky if we got rough estimates for most numbers, but with WMAP, we started to really nail everything down. There was a lot less doubt about the details of cosmology after WMAP than there was before. Some of the things it measured were the age of the universe, how fast the universe had been expanding, how many protons and neutrons were in the universe, how much total matter was in the universe. And it started to provide us with support that the very beginning of the universe had an era of cosmic inflation that we've talked about in other episodes. All of these things came into focus because of WMAP. Starting around 2007, some other telescopes started to study the cosmic microwave background from the ground. So instead of balloons or satellites, these are the South Pole Telescope and the Atacama Cosmology Telescope in the South Pole and Chile, respectively. These had much higher resolution than what you could do from space, but you wouldn't look at the whole sky. You'd look deeply in some particular patch of sky. So it was kind of complementary to the satellite-based measurements. And then the big player today or in recent years has been the kind of successor to WMAP called Plonk, the Plonk satellite. They've been taking data between 2009 and 2013. They basically did what WMAP did, but even better resolution, everything you wanted in a satellite-based cosmic microwave background experiment. Plonk pretty much was it. Let me give you an idea of how much precision you get with an experiment like Plonk. So Plonk tells us the density of protons and neutrons in the universe to 0.6% precision. It tells us the amount of dark matter in our universe to 0.8% precision. So these are better than 1%.
And it also tells us about the Hubble constant, basically how fast our universe is expanding. And it tells us this to about 0.6% precision. Though this value is a little controversial. We'll get into that another time.
Planck measured the age of our universe to 0.15% precision, or 13.787 billion years. It's just amazing that we know that number, not just kind of approximately, but we know it to, lots of sig figs. It's amazing to live in this time. And then, of course, all sorts of other stuff came from this too. We learned a lot about inflation, or a lot of support for inflation from Planck. We managed to learn things about how much radiation there was in the early universe, things like this. All sorts of measurements came from this vast data set. I probably look up details in terms of the Planck measurements like every few days in my job. It's like a repeated exercise. I have the Planck collaborations, cosmological parameters paper kind of on my speed dial, if you will. So cosmologists aren't done with the CMB. We still have pretty ambitious plans to measure it even more precisely in the like roughly decade-ish scale. We're looking forward to something called the Stage 4 CMB experiments maybe. These will be ground-based, probably a combination of telescopes in Chile and the South Pole, a really big array of telescopes. The kind of big goals of Stage 4 CMB are to precisely measure how much radiation there was in the early universe. This might tell us about exotic forms of matter that existed, or maybe exotic things that might have happened involving neutrinos in the early universe. Also, there's this ongoing problem with what we call the Hubble tension. So the rate at which the universe has been expanding, we measure in different ways and we get different answers. This might resolve that problem, or at least shed some light on it. We hope so. And then, of course, the big elephant in the room of cosmology is to understand inflation and, well, really convince us that it happened, and then learn the details of how it happened and why and what drove it. And we're looking for specific signals here in the CMB that will give us like telltale signs of inflation. These are the sorts of things that we think this next generation of telescopes can see in the cosmic microwave background that will help us piece together this really exotic era that happened a tiny fraction of a second after the Big Bang.
Why This Universe is brought to you by the University of Chicago Podcast Network. This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago, and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.